Hey everyone, and welcome to the channel. Artificial intelligence and machine learning are changing the world, and at the heart of this revolution are massive clusters of GPUs. But here's a multi-million dollar question. You've just invested in 1024 powerful GPUs. How do you connect them so they can actually talk to each other without bottlenecks? Because if your network is slow, your GPUs will be sitting around waiting for data, and your week-long training job could stretch into a month, or even fail completely. That's a massive waste of time and money. Today, we're going to solve that. We're diving deep into the Cisco blueprint to design a powerful, efficient, and lossless network for a 1024 GPU cluster. We'll figure out exactly how many servers, racks, switches, and links you'll need. Let's get started. First things first, let's establish our foundation. Our goal is a 1024 GPU cluster. The Cisco design blueprint uses servers that each contain 8 GPUs. This is a very common configuration for high-density AI systems. So the math is simple. We need 128 high-performance servers. Now, where do we put them? In racks, of course. A standard data center rack is 42 units tall. These GPU servers are beefy, often 2U or 4U high. Let's assume we can comfortably and safely fit 8 servers in each rack. So we're looking at a setup of 16 racks to house our entire GPU cluster. But the most critical part is how these servers talk. Each server in this design is equipped with two 100 Gbps network interface cards, or NICs. Why two? Redundancy and performance. This means we have a grand total of, that's our connectivity challenge. How do we wire up 256 high-speed links without creating a traffic jam? The answer lies in a classic and incredibly effective network design, the spine and leaf architecture. The leaf layer is the first point of connection for our servers. Think of them as the on-ramps to our network highway. Our goal is to create what's called a non-blocking fabric, which means the switches have just as much bandwidth going up to the rest of the network as they have coming in from the servers. For this, the blueprint suggests a powerful switch like the Cisco Nexus 93600 CDGX. Let's look at its specs. It has 28 ports that can run at 100 Gbps for connecting our servers. And it has 8 uplink ports that run at a massive 400 Gbps each for connecting to the core of our network. So, how many of these leaf switches do we need? We have 256 server connections to make. The design calls for 10 leaf switches. This setup provides redundancy. Each server is dual-homed, meaning one 100 Gbps NIC connects to one leaf switch, and the second NIC connects to a different leaf switch. If one switch fails, the server can still communicate through the other. This is absolutely critical for long-running AI jobs. With 10 switches, we have 280 available 100 Gbps ports, which is more than enough for our 256 server connections, leaving us some spare capacity for storage or other infrastructure. Now for the backbone. The spine layer is the superhighway that connects all our leaf switches together at incredible speeds. The rule of a spine leaf design is that every leaf must connect to every spine. Let's calculate the bandwidth we need. We have 10 leaf switches, and each one has 8 uplinks running at 400 Gbps. We need a spine layer that can handle 80 connections at 400 Gbps. For maximum performance and resiliency, the blueprint recommends using 4 spine switches. The model of choice here could be the Cisco Nexus 9332 DGX2B. Each of our 10 leaf switches will connect to all 4 spine switches. With 8 uplinks on each leaf, they will send two 400 Gbps links to each of the 4 spines. This full mesh connectivity ensures there's no single point of failure and provides a huge amount of bandwidth. Traffic from a server on rack 1 can get to a server on rack 16 in just 2 hops, leaf to spine and spine to leaf. This keeps latency incredibly low, around 4.5 microseconds across the entire fabric. So let's recap the final blueprint for our 1024 GPU cluster. Servers, 128 servers, each with 8 GPUs. Racks, 16 racks, each housing 8 servers. Leaf switches, 10 Cisco Nexus switches, providing 256 plus ports of 100 Gbps connectivity. Spine switches, 4 Cisco Nexus switches, creating the 400 Gbps core backbone. Server links, 256 links running at 100 Gbps. Fabric links, 80 links running at 400 Gbps connecting the leaf and spine layers. This is a true non-blocking fabric, but what makes it lossless? AI workloads use a protocol called ROCEV2, that's ROCEV2, which is extremely sensitive to packet drops. Even a single dropped packet can cause delays and hurt performance. This network design uses two key technologies to prevent drops. ECN, explicit congestion notification. This allows switches to mark packets to gently tell servers, hey, things are getting a bit busy, maybe slow down a little, before they have to drop anything. PFC, priority flow control. This is the safety net. If things get really congested, a switch can send a pause frame to the upstream device, telling it to hold on for a moment to prevent any packet loss. When used together, ECN and PFC create an intelligent, self-regulating network that avoids packet drops, ensuring your AI jobs run as fast as possible. Now, for some of the most demanding AI workloads, even 100 Gbps to the server isn't enough. For these, you might build a completely separate dedicated back-end network just for GPU to GPU communication, running entirely at 400 Gbps. How does our design change for that? Well, it scales up significantly. According to the blueprint, a 1024 GPU cluster with direct 400 Gbps connections would require 128 servers, still 8 GPUs each, 32 leaf switches, 16 spine switches. Each leaf would connect to every spine with 2 x 400 Gbps links. This is an absolute beast of a network, designed for the most bleeding-edge AI research and development where every microsecond counts. So there you have it. From servers and racks to leaf and spine switches, that's the professional blueprint for building a network that can keep up with a 1024 GPU AI factory. The key takeaways are: start with your server and GPU count to define your ports. Use a two-tier spine and leaf architecture. Design for a non-blocking fabric with high-speed uplinks. And implement congestion management like ECN and PFC to create a truly lossless network. Manually configuring all of this would be a nightmare, which is why tools like Cisco Nexus Dashboard Fabric Controller exist to automate the entire setup, ensuring it's done right and without errors. And for visibility, Nexus Dashboard Insights helps you monitor for congestion and optimize performance. I hope this breakdown was helpful. Building AI infrastructure is complex, but with the right blueprint, it's totally achievable. If you learned something today, hit that like button and subscribe for more deep dives into data center tech. Let me know in the comments what kind of cluster you're dreaming of building. Thanks for watching, and I'll see you in the next one.